How does DMA achieve lightning-fast data transfers in embedded C? Imagine a busy highway where cars move smoothly without stopping at every traffic light. That's similar to how direct memory access, or DMA, speeds up data movement in embedded systems. Instead of the CPU handling each tiny step, DMA acts like a dedicated courier, transferring data directly between peripherals and memory. This means the CPU can focus on other tasks, making the whole system faster and more efficient. In embedded systems, the CPU usually manages data transfers by reading and writing data one piece at a time. This process takes up a lot of CPU time and slows everything down. DMA bypasses this by having a special hardware controller that takes over the transfer process. First, the CPU sets up the DMA controller by telling it where to get the data from, where to send it, how much data to move, and how to do it. Once configured, the DMA controller takes control of the system bus, which is like the main road connecting all parts of the system. When a peripheral device, like a sensor or a communication port, needs to send data, it sends a request to the DMA controller. The controller then asks the system bus for permission to take control. Once it gets the green light, it moves the data directly from the source to the destination without bothering the CPU. This process is quick because it avoids the usual back and forth that the CPU would have to do for each byte or word. DMA supports different transfer modes to match different needs. In burst mode, it transfers large blocks of data all at once, which is great for speed but temporarily blocks the CPU from using the bus. Cycle stealing mode transfers one data unit at a time, sharing the bus with the CPU to keep things balanced. Transparent mode only transfers data when the CPU is idle, so it doesn't interfere with ongoing tasks but might be a bit slower. From an electrical engineering point of view, DMA reduces the number of bus cycles the CPU has to execute. This lowers power consumption and makes the system more responsive. It's especially useful in real-time applications like audio streaming or sensor data collection, where quick data handling is essential. In embedded C programming, using DMA involves setting up the DMA controller registers with the right addresses and transfer sizes. You also enable interrupts to know when the transfer is complete. This way, the CPU can keep working on other things while the hardware handles the data movement. It's like having a smart assistant that takes care of repetitive tasks so you can focus on more important work. In summary, DMA makes data transfers lightning fast by letting hardware handle the movement directly. It reduces CPU workload, speeds up data flow, and makes embedded systems more efficient. This is why DMA is a key feature in high-performance and real-time embedded applications programmed in C.